Hello, I present for you an experimental paper in which we have studied the impact of sampling on label propagation based graph partitioning. As you know, graph data is used more and more in several applications as it allows a better representation for data structure than other kind of data modeling like relational database. It can be used to model relationship in social data, social media data, and also to model the road network and many other kind of application. The size of this data is very massive and every day it's become more and more bigger. So to analyze this data, we need to use an efficient system, mainly to use a distributed graph processing system in which we partition the graph on several machines and we run the analysis to make it faster. But the partitioning task of a graph, it's not a simple task because it needs to take into account several constraints. Mainly to optimize the quality of partitioning, we have to balance the partition on the different machine because an unbalanced partitioning can lead to a imbalance in the load of each machine and can slow down the processing. Also, we have to take into account the quality of edge cuts, which means the number of connection and edges between different partition, because a higher edge cut can slow down, can increase the interconnection between the partition and slow down the processing. So we have to take into account these constraints when partition the graph data. In this paper and our work, we have studied the sampling impact on label propagation based partitioning algorithms. Mainly, we have proposed two sampling heuristics to improve the propagation process and the partitioning algorithm, and we have extended an existing work that we have presented previously and propose to take into account the edge or the vertex balance of the partition of the graph. And we have evaluated our sampling heuristics basing on the quality of the partitioning, on the quality of edge cut, the balance, and also we have studied the robustness of the parameter of the sampling. So in this work, we focused mainly on improving the initialization step of the label propagation-based partitioning by introducing the graph sampling. In fact, the initialization is a crucial step in our algorithm. It has been proven also in previous work that the quality of initialization can dramatically impact the performance. We have proved also in our paper, previous paper, that a simple improvement and optimization of the initialization step of the label propagation had led to a better quality of the partitioning and to reducing the computation time. In this paper we tried to improve this step by integrating the graph sampling. Why the graph sampling? Because it allows us to obtain a smaller graph that preserve some property and some embedded structure in the main graph, and it can lead to better results. So we try to prove experimentally our hypothesis about the good impact of the sampling on the label propagation partitioning, and we have made several experiments using different kinds of graphs that have different structure and characteristic. And experimentally, we have showed that the sampling has a good impact regarding and comparing to the original label propagation algorithm. In particular, we have improved the label propagation computational time by reducing this time with again that range from 6 to 40% over all the graphs. Regarding the partitioning quality, it was almost stable either for the balance quality or the edge cut quality, and we have observed some slight improvement on some graphs for the edge cut quality. I will give more detail about the results in this presentation, but you can also refer to our paper to have more details about the approach and the results. So, as I have introduced before, in our paper we extended a previous work called B-GRAP. B-GRAP is a parallel label propagation partitioning algorithm that can deal with either edge balance or vertex balance constraint. This algorithm proposed a parallel version of the label propagation, which has been extended to partition a graph on a distributed processing system, and we have modified the initialization step comparing to the main and the basic label propagation by taking into account only the vertices, which means we take into account only the vertices with highest degree. And we have proved experimentally that this optimization, as I explained before, allowed us to get better results than the original algorithm, and also to comparing to other similar algorithms that use the label propagation approach. So we have introduced two sampling heuristics as initialization for the label propagation partitioning algorithm B-GRAP. The first one is HDB-GRAP and the second one is RDB-GRAP. We differentiate in the sampling two steps. The first step, which is the seed selection, and the second step, which is the sampling. In the seed selection, in the HDB-GRAP, we select some seeds by choosing the highest degree vertices, and in RDB-GRAP, we choose the vertices randomly. Then, in the next step, in the sampling, we try to explore the neighborhood of each seed by choosing the same number of high degree vertices from the neighbor of each seed, which allow us to avoid that all samples being chosen from the hub vertices neighbor. And then in the final step, we give the sampler graph as an entry for the partitioning approach, and we proceed by using the label propagation in order to partition the graph. Now I will explain how our label propagation partitioning approach works. So first we start by initializing the algorithm by choosing some vertices using one of the initialization strategies that I have presented before. And then we give a unique label for each of these vertices, and we proceed to the next step in the algorithm, which is the label propagation step. In the label propagation step, each label of the initialized vertices will be propagated to the neighbor of this vertex, and then each of these neighbor will update and propagate iteratively his label basing on the most frequent label that he has received, the vertex has received from the neighbor, and using a particular objective function that take into account a penalty term, and in this penalty term we can choose between either edge balance, vertex balance, and edge cut quality. And finally, the algorithm will iterate until the convergence, and once we have the convergence, we obtain the partitioning graph. Now I will give some detail about our experiments that we have done in order to evaluate the sampling heuristics. So we have chosen 9 datasets with different size and degree distribution from social network, web graphs, and synthetic graphs. As we can see, for example, Wikitalk. In Wikitalk graph, we have the most of vertices has a degree less than 1. And on the other side, if we look to the Twitter graphs, with the largest graph that we have used, the maximum degree can attain more than 4 million edges for one vertices. And then to do the experiments, we have used a cluster of single nodes, and for each algorithm and each graph, we have run 10 execution by using different value and different number of partition. And for this this execution, we have compute the average of different measures, mainly the maximum normalized balance that measure the quality of balance, and the percent of each cut, and the computational time required to complete the label propagation processing. In the experiments, we have studied the impact on the edge balance quality, on the vertex balance quality, and we have studied also the robustness of our algorithm to its parameters. In this table, I present the summary of the results that we have obtained for the vertex balance case. This table presents the percent of improvement of quality and performance with respect to the B-GRAP algorithm. The first column, the MNU evaluate the vertex balance, and the other column represents the edge cut quality and the label propagation time. As we can see, regarding to the balance quality and the edge cut, the improvement is almost near to 0%, which means the result and the quality are stable. Regarding to the label propagation time, we can see for both highest degree B-GRAP and RD B-GRAP, the percent is very high, which means the sampling has a very good impact on the label propagation time. Regarding to the edge balance case, we can say the same conclusion. The balance quality and the edge cut quality is almost stable, with some exception on few graphs. And regarding to the label propagation time, we have also the same conclusion. We have an improvement that ranges between 8 and 40% on all the graphs. Which means that the sampling has a good impact on the label propagation processing time. So on this slide, I summarize the results that we have obtained by studying the parameter robustness of our different heuristics, sampling heuristics. I present only the result for Twitter graph. On this slide, we have varied the sample size, and we studied the impact of sample size on the computation time. And we varied the sample size between 10 and 25% of the total size of the graph, which means the total number of vertices in Twitter graph. As we can see, for both heuristics, either HD B-GRAP or RD B-GRAP, with a sample size equal to 10%, which means a small value of sample size, the computation time is high, either for the label propagation or the time required for the sampling. And we obtain the better results and the better computation time for a sample size equal to 20%. So we can conclude that we can set a small value. It's not very efficient on the partitioning, but a value equal to 20% can be used as and set as a default value to our algorithm, which help us the user, which help also the user to set less parameter in entry of the algorithm. So to summarize, in our experimental paper, we have introduced two different heuristics based on the sampling in a label propagation partitioning based algorithm, and we have showed experimentally that the sampling have a good impact on the partitioning, either for the time, computation time, or the quality of the partition. In particular, we have proved that experimentally that the label propagation time using the sampling was reduced with a gain between 6 and 40% over all the graphs. The balance quality was generally stable. Similarly, for edge cut quality was generally stable, with some slight improvement for a few graphs. In the future, we want to benchmark our different heuristics on more massive graphs, and we want to study the impact of our algorithm on the graph analytic algorithms by using the partitioned graph as an entry to these analytic algorithms. And we want also to extend our implementation and initialization to solve community detection problem. In fact, some of community detection algorithms are based on the label propagation, and we want to study the impact of our heuristics on the community detection based on LP approaches. For more details about our works, current works, and previous work, you can refer to our papers. And thank you, everyone.